Hey math fans, we're on section 2.3.1. Let's get started. In this section, we're going to be building functions from different contexts. And in order to build a quadratic, we need to identify what the important information is. And most often, we will be drawing a picture. Here are some of the key concepts. Remember, we have the different forms. One of the most popular is the vertex form because that shows you exactly where the maximum or minimum of the quadratic is. Concavity is important. So if you're concave up, there's a minimum. Concave down, there's a maximum. And here are some common misconceptions. Remember that the leading coefficient is really going to determine whether or not you're concave up or concave down. Example 1 says a farmer is building a rectangular pen using 100 feet of electric fencing. Now, the fence is going to be on the side of a barn, and they want these 4-foot gates on both sides of the fence. So I've drawn the barn here. Here's one fence and there's the other fence. Now, these two sides of the fence will have this little 4-foot wide gate, which will also include in the 100 feet of electric fencing. And then you're going to have the leftover. So you have x plus 4 and x plus 4 because we don't know how much fence that's going to be. And then we have the leftover fence because we have 100 feet of the electric fencing. And so we have this leftover amount, which means it'll be 100 minus these two sides. And so if we have x plus 4 and x plus 4, it's going to be 100 minus 2 times the quantity of x plus 4. And then if we simplify that, we get 92 minus 2x. From here, let's talk about how to build the function. And it's going to be an area formula. In other words, length times width or base times height. And we have the length is x plus 4. We have the width is 92 minus 2x. We're just going to multiply these two together. And so notice how here I have them substituted. We will double distribute when we multiply. And then we have our final area quadratic, which is negative 2x squared plus 84x plus 368. We want to know for what value of x is the area going to be the largest. So that would be the vertex. If we were to graph this, we would notice it would be a concave down or it'd be opening downward. So we will have a maximum area at the vertex. So we're going to use the negative b over 2a formula. We get positive 21. This positive 21 says that when x is equal to 21, that will give us the maximum area possible for the area inside the fencing. And so how do we know what that maximum area is going to be? Well, we just substituted in for x. So we have a of 21, and we finally simplify this and we get 1,250. So the maximum area is going to be 1,250 square feet. Here's a drawing of the quadratic. Notice it's concave downward. We have our vertex at 21, 1,250. But we still haven't figured out what is the whole entire side length and the width of this pen. We have to substitute back in when x is equal to 21. We're going to substitute 21 plus 4. So basically each of those sides will be 25 feet. And then the final side should be 50 feet. And that will get us the maximum area possible. Example 2 says an amusement park has commissioned the design of a steel roller coaster. Now this roller coaster is going to drop and it's going to actually go below the ground. I don't know if you've been on a roller coaster that goes underneath the ground or below the ground level. And it gives a couple of horizontal distances. So this is best done when you draw a picture. So here's my picture of a roller coaster that I stole from the interweb, but more often you will be drawing a picture that looks like this. So I have the red line squiggle is basically the roller coaster. And so after 24 feet, it's going to enter underneath the ground. And then at 36 feet, it's going to exit underneath the ground. And the lowest point is going to be 12 feet beneath the ground. And what I want to do is I want to build a quadratic. Notice this is going to be a concave up quadratic. And the point I'm going to use, or the points I should say that I'm going to use, are the x-intercepts. If I make the top of the roller coaster, or when it starts to go downward at x equals 0, I'll say that it enters underneath at 24, 0, and then it exits at 36, 0, which means the vertex is going to be halfway in between those two. So I'm going to add together 24 plus 36, divide by 2, and I get 30. So I actually have the vertex there of 30, and then I know it's 12 feet beneath the ground level, so it's negative 12. What I'm going to do now is substitute those values into the factored form. Remember, it's x minus whatever the intercepts are for each of the parentheses. The problem is that I don't know what a is, and so we're going to have to come back to a. So we double distribute, and we can get this quadratic, but we still don't know what a is. Well, we're going to need a third point, and it doesn't matter which point you use, but it's going to have to be something other than the 24 and the 36. So let's use the vertex. The 30, 12, that's an x value of 30, a y value of negative 12. We're going to substitute that into this quadratic equation. So when we substitute this in, we get negative 12 equals a, parentheses, 30 squared minus 60 times 30 plus 864. We're just going to solve for a. And we're going to get a is equal to 1/3. And there you have it. We have the a value, and then we also have the rest of that quadratic, x minus 24, x minus 36. So that's our final equation for this part of the roller coaster. Now, if we want to find the height of the peak of this section of the roller coaster, remember we made the absolute maximum height there at the beginning when it first started to dip at when x is equal to 0. So let's substitute 0 in. We're basically finding the y-intercept, and we get y is equal to 288. Here's a picture of the graph on the right, and the y-intercept will be at 0, 288, and I have all the other points drawn as well. Example 3 says, each side of a suspension bridge has a cable that's secured at either end. The cable's lowest point is 15 feet above the surface of the bridge. The towers are 400 feet apart, and the vertical distance from the surface of the bridge to the top of each tower is 415 feet. Again, draw a picture. And I think the best strategy for this one is let's use the vertex, or put the vertex on the y-axis. So I have my bridge right here, and then the cable extends down, and don't forget what these numbers are. So we're going to actually make the vertex here 0, 15, because it's going to be 15 feet above the ground. And then because they are 400 feet apart, one of these towers, the top point will be negative 200, and the other top point will be at positive 200 for x. And remember, it's 415 feet for the y. And so all we have to do here is use the vertex form, and we're going to substitute in 0, 15 into the vertex form of a quadratic, and we get y equals ax squared plus 15, and we still don't know what a is, so we're going to have to use a third point. And it doesn't matter which one you use. So let's just use 200, 415, and we're going to just substitute it into that quadratic, and we'll just solve for a. And once we got a, we've got the entire equation. When we simplify, we get a is equal to 1/100. Final answer will be y equals 1/100 times x squared plus 15. And that's going to do it for this section. We'll see you in class.